for electrical conductivity. So electrical conductivity, as we know, is the ability of a conductor to allow or permit the electrical current through it. Okay, that ability of a conduction of electric current is called electrical conductivity of that material. We know the conductors allows, or the metals generally are the good conductors of electricity. So we will calculate the or derive the expression for electrical conductivity by considering the material as a metals, okay, or the conductors. For that, let us consider the piece of metal having cylindrical shape, having length capital L, and area of cross section of the that cylindrical metal block is a capital A. Okay, suppose the potential difference V is applied across the metal, and whenever the potential difference is applied to the metal block, we know the current is flowing through the metal. Again, the electric field is developed across the two ends of the metal, because the as soon as the potential difference is applied, the opposite charges were accumulated on two surfaces or two ends of the metal, that will produce the electric field in that metal. So the electric field E can be written as electric field E equals to potential per unit length, means E equal to V upon L. Therefore, the potential developed or potential applied can be written as V equal to E into L. That is our equation number 1. As the potential is applied, the current is flows in the external circuit, again through the metal also. Suppose if R is the resistance offered by metal to the flow of current, therefore I equal to V upon R. Okay, from the Ohm's law we can write V equal to I into R. Therefore the current through metal or current in the circuit, I equal to V upon R. Okay, put the value of V from equation number 1, which is E into L. So equation becomes I equal to E into L upon R. That is our equation number 2. Okay. Now we know from the general expression for resistivity of a metal, or the in general the resistivity of metal R, or the resistance of metal R, is directly proportional to length of the that conductor or metal. Okay, actually in practice the resistance offered by any material or in the metal is always directly proportional to length of the that conductor or metal. And inversely proportional to the area of cross section of the that material. Okay, so R is proportional to L by A, and if we remove the sign of proportionality, put here equals to and some constant, and that constant is rho, and the rho is called specific resistance or resistivity. Okay, it is the general expression for resistance which is applicable for any material. Okay, that means the resistance offered by any material is always directly proportional to length of the that material or conductor or metal, and inversely proportional to area of cross section. Means if the area of cross section is more, means if we use the conductor or any wire having more area of cross section or more thickness, then it offers less resistance. Okay, therefore in electrical appliances or domestic appliances where the high power is required, in such cases we use the thick wire. Okay, and whenever there is a necessity of less power or less power consumption for the particular domestic instrument, then we use the thin wires. Okay, because the broad wires are having more cross sectional area, will offer less resistance. Okay, so put the value of this capital R in equation number 2 in place of the R. So I can be written as I equals to EL upon rho into L by A. Here L from numerator and L for denominator got cancelled, and A is sent on numerator side. So the equation became E into A divided by rho. If we take this A on denominator side of LHS, the equation becomes I upon A equals to E by rho. Okay, that is our equation number 4. So this I by A ratio of current to area. Current to area means current density. Current density is equals to electric field per unit resistivity. Okay, now here we can define the current in terms of current density J as, we can define the current density in terms of the current as I equals to integral sign J into dA. J is constant quantity, take out of the integral sign. So in integration of dA, and integration of dA is A. So this A is sent on LHS toward the LHS. So equation becomes I by A equals to J. As I have told you already about this current ratio of current to area is called current density. But this actual definition of current density. So current is the integral of current density over the small area dA. Okay. Now put this value of J equals to I by A in equation number 4. Oh, let us see the equation 4. Here equation 4 is I upon A equals to E by rho. So in place of I by A, we have substituted J. Therefore, J equals to E upon rho is our final equation. Okay. So J equals to E by rho, but we know 1 by rho is called sigma, that is the electrical conductivity. So electrical conductivity is always reciprocal to electrical resistivity. Okay, so resistivity means it is the factor which or ability of any conductor or any material to oppose the flow of current through it. Okay, and electrical conductivity is the ability of a material or conductor to allow the current through it. Okay, therefore both have opposite tendencies, and hence reciprocal of resistivity is called conductivity. So in place of this 1 upon rho in this equation, we will substitute sigma. So the equation becomes J as it is. In place of 1 by rho, we have substituted sigma, and E kept as it is. So J equals to sigma E. This implies sigma can be written as J upon E. Equation number 6. Just remember all these simple calculations, because this expression is much bigger, but the terms or the physical quantities which are used are very simple, and I think you have already studied about these physical quantities. Okay, just we have to focus on your final target, and for achieving this, just made the simple calculations. Okay, remember the steps, step by step expression. So up to the equation number 6, we have calculated the expression for electrical conductivity in terms of current density and E, where E is a known quantity, but we have to calculate or solve for the current density. Okay, so let us solve for current density. Now, uh, we know as soon as the potential is applied or potential difference is applied to the block of the conductor, then the electric field will be developed across the two ends of the conductor. So in an electric field, what happens? The electron which causes the current will experience the force. Okay, that means force is experienced by the electron in an electric field, that is called electric force experienced by charge particle having charge E is equals to small e into capital E, where small e is the charge of electron and capital E is the electric field applied to the that metal or conductor. Okay, so here E into E is the force experienced by sorry, charge particle. So due to the force, the motion of electron is disturbed or affected. That means the electron got accelerated, and hence this acceleration of electrons will be force per unit mass, because we know from the Newton's second law the force equals to mass into acceleration. So acceleration can be written as ratio of force to mass. Okay, means here acceleration a of the electron equals to a equals to force, that is E into E divided by the mass of electron m, where m is the mass of electron. Okay, so it is about the acceleration produced in the electron due to the application of external electric field. Okay, now we know, in general case, according to the assumptions of Drude-Lorentz free electron theory, the electron moves in a random direction inside the entire volume of that metal or conductor. Okay, and due to its random motion, there are chances of collision. So every time the electron collides with the other electrons, also they collides with the walls of the that metal. Okay, so after collision, the electron starts moving in new direction. Okay, because the motion of electrons inside the metal is a Brownian motion. I will draw here some kind of motion. So electron suppose initially starts from this position and it is moving in this direction. Direction of arrow indicates the direction of motion of electrons. And suppose at this position there is other electron, so it may collides with the other electron, therefore after collision it changes its direction. Okay, and the second electron maybe moves in another direction. So after every collision, the electron starts moving in a new direction with zero initial velocity. As soon as it collides with the other electron, its velocity or the electron stops for the certain moment. Okay, for a few very few time, the electron stops and it starts moving in other direction. Okay, with zero initial velocity. As soon as electron stops during the collision, its velocity decreases to zero for very small interval of time, and again it moves in another direction with another velocity. Okay, so after collision, electrons velocity became zero, having zero initial velocity, and it acquires some velocity or energy due to the collision, and it moves in a new direction. Okay, again the electric field is also applied to the metal, so the electrons acquires velocity due to the electric field. Okay, so this velocity acquired by electron depends upon the force experienced by electron. Due to the force, how much is the acceleration producing the electron, and we know this velocity acquired by electron is equals to, here just see the expression for acceleration and velocity. We know acceleration equals to velocity upon time. Okay, change in velocity with respect to time is called acceleration. So velocity will be product of time and acceleration. Okay, so in this case, due to the electric field, this much amount of acceleration is produced in the electron, and hence the velocity acquired by electron v equals to product of this acceleration and the time interval between two collisions, that is tau, denoted by tau. Okay, so equation 7 gives you the velocity acquired by electron due to the electric field having time interval between two collisions as a tau. Okay, so with this new velocity electron moves in a new direction. Now let us calculate the average drift velocity or average velocity possessed by electron due to the application of electric field. So for calculating the average velocity, or it may be called the average drift velocity, because due to the application of electric field, the electron orients in a direction opposite to the electric field. That motion or that orientation is called drifting, and the velocity of drifting is called drift velocity. So drift velocity or average drift velocity will be mean of initial velocity and final velocity divided by 2. Here we know as soon as the electron collides with the each other, or it collides with the walls of the conductor, it possesses zero initial velocity, and the final velocity achieved by electron due to the electric field will be E into E upon m into tau. Okay, so it will be E sorry, E upon twice m into tau. That is our equation number 8. So equation 8 is the expression for average drift velocity possessed by electrons due to the application of electric field. Okay, as in the Drude-Lorentz pre-electron theory, the assumptions made by Drude and Lorentz, we mentioned here, we have seen that the drift velocity achieved by electron is superimposed over the already existing velocity. Okay, now just superimpose that velocity and let us see what happens. Okay, but before this, the quantity E into tau, let's see, the E into tau upon 2m in equation 8 is called electronic mobility, mu E. So E tau upon 2m in the equation 8 is mu E, that is electronic mobility, ability of electron to move under the application of electric field, that is called mobility. So replace this E tau upon 2m by mu E. So equation 8 changes to the form Vd equals to E capital E, which is remains here, into mu E. That is our equation number 9. Okay, so up to 9 all the things are very simple. Now move towards the further part of the expression. So if, just imagine the drifting of electron is equal to the length of conductor. Means just see here, due to the application of electron, the electron orients throughout the length of conductor. Okay, that means as soon as the electric field is applied, or as soon as the external potential is applied, the electron moves or drifts from one end to the other end of the conductor. Okay, means if the average drift velocity of electron is equal to the entire length of the conductor. Okay, therefore the volume of metal, as we know, the volume of metal is a cylindrical shaped here like this. It is one of the cylinder having area of cross section as a capital A and the length of conductor L. We know the average drifting of electron is throughout the length, means L is equals to Vd. So volume of cylinder will be length into cross sectional area. So it will be A into Vd. Okay, and the number of electrons will be here n, small n is the number of electrons per unit volume, means in a 1 meter cube or 1 centimeter cube, suppose n number of electrons are present. Okay, therefore the total number of electrons will be number of electrons per unit volume into the total volume of that conductor. Okay, so the number of electrons present in the conductor will be n into A into Vd, where small n is the number of electrons per unit volume. Just see here, just remember the n. The n is the number of electrons per unit volume, and A into Vd will be total volume of conductor. Okay, total volume of conductor. So the total number of electrons are n into A into Vd. Okay, just see the, we know the number of charges in the conductor will be n into A into Vd. Okay, but we know current equals to number of charges flowing per unit time. Okay, or the number of charges crossing a particular cross section is n into A into Vd, or total number of charges will be n into A into Vd. And if we multiply the number of charges by charge of each charge particle, then we will get the total current through the particular cross sectional area. Okay, so n into A Vd into E will be the total current or net current through the that any end of the conductor. Okay, so in that, send this A on other side, so equation becomes I by A equals to n into Vd into E. But we know ratio of I upon A, that is current upon area, is called current density. So replace here J, I by A by J, so J equals to n into E into Vd. That is our equation number 10. Okay, but we know Vd equals to, just see the previous equation, Vd equals to E into mu E from equation 9. Okay, so put in place of Vd, just substitute E into mu E. Okay, so equation becomes J equals to E n into E into E into mu E. Okay, so from this equation, sometimes whenever they ask to derive the expression for Ohm's law in case of electrical or in case of metals, then you can mention here, or you have to derive up to this equation. So in that equation, n, that is number of electrons per unit volume, is constant. E, that is charge of the charge particle, is constant. Mu E, that is equal to E tau upon 2m, which is also constant. So we can write here J proportional to capital E, or J proportional to sigma. So here we can prove the Ohm's law in electrostatics, or in electrical conductivity, in case of electrical conductivity. So again solve or simplify the equation. Here send this E on other side, so E upon J upon E equals to NE into mu E. But we know J upon E is equal to electrical conductivity. Just see the previous equations. Here equation 6, sigma equals to J upon E. Okay, So put the value of this J by E equals to sigma in equation number 10. Okay, so J upon E equals to sigma, therefore above equation becomes sigma equals to Ne into mu E. Okay, again we know mu E equals to E tau upon 2m. Just see the previous equation here. E tau upon 2m equals to mu E. Again put this value, so equation becomes, just multiply this Ne by E tau upon 2m. So it becomes n as it is E into here this E, that is E square tau as it is upon 2m. So sigma equals to n E square tau upon twice m. That is our equation number 11. Okay. So again we know the mean free time, that is time required to electron between two successive collisions. Time equals to length upon or distance upon velocity, because we know velocity equals to distance upon time. Okay, we always know velocity v equals to length or distance, that is called the mean free path length upon time, tau. So time can be written as tau equals to lambda upon v. Okay, put the value of this tau in equation number 11. So equation becomes n e square as it is. In place of tau we have substituted lambda upon v. So equation becomes sigma equal to n e square lambda upon 2mv. That is equation number 12. Okay, again we know the average kinetic energy of an electron is Ke equals to 3 by 2 kT. So average kinetic energy possessed by electron at temperature or at any absolute temperature T, it is always equals to 3 by 2 kT, where K is the Boltzmann's constant and T is temperature in Kelvin or any absolute temperature. Okay, also we know the kinetic energy can be written as half mv square, where m is the mass of electrons and v is the average velocity of electrons. Here 2 from LHS and RHS got cancelled, and we send this m on other side, so it becomes kT upon m. And take the square root, solve for v. So v equals to under root of 3 kT upon m. Now substitute this value of v in the equation 12. It is equals to n e square lambda upon 2m as it is from equation 12, and in place of the v we have substituted 3 kT upon m. Again send these two in the inside the square root, it becomes m square. So equation becomes 3 kT m square upon m, where mm got cancelled, and the equation becomes under root of 3 kT m. Okay, so expression becomes sigma equals to n e square lambda upon 2 under root of 3 m kT. Okay, so this is the expression for electrical conductivity of metals. And we know, we can see that the sigma depends upon number of charge particles per unit volume, which is constant. Again, E square charge of the charge particle is constant. Lambda, that is mean free path length. So distance between two consecutive collisions, that is called the mean free path length. Okay, and it is inversely proportional to mass of the electron, Boltzmann constant and temperature. Okay, so one can write here sigma inversely proportional to 1 by under root of t. So it is about our today's expression. Okay, so thank you very much. Now you can ask me any difficulty about the topic, today's topic. Anybody has any difficulty, you can ask me.